Hello, let's look at this question. So this one, example question 3, which is another cost-minimization problem. Okay. The fast food restaurant currently pays $4 per hour for service and $8 per hour for rental machinery. The production function of this restaurant is Q equals to K squared by L squared. This is page 10 of slides 23. Okay, so now I'm gonna switch to my document camera for a clear demonstration of this problem. You're strongly advised to refer to the slides for the detail of the question itself. So here, a fast food restaurant currently pays $4 per hour, so W equals to 4, and $8 per hour for machinery, so R equals to 8. Okay, so in here, as I strongly advised, please write down those questions into its math notation, which will facilitate your future exploration. Now, the production function Q equals to K squared L squared. Now, what is the marginal product of labor and capital? Marginal product of labor, it is partial derivative of Q with respect to L. Okay. And here, that is to say, you recognize L as the only variable. K squared is a constant multiplied to this variable. So we have partial derivative of K squared by L squared with respect to L. So here, according to the constant multiple rule, which is K by Fx, its derivative equals to K by the derivative of Fx. And here, K squared is like the K here, right? It is a constant multiply. So we just write it out. K squared multiplied by the derivative of L squared with respect to L. And here we're gonna utilize the derivative of the exponential function. And the derivative of L squared with respect to L is 2L. So the result is 2K squared L. We just move 2 to the frontal part. And then marginal product of capital is partial derivative of Q with respect to K. Namely, you're treating K as the constant, as the variable, and L squared as the constant. So we put the constant ahead. So in this case, it's partial derivative of L squared K squared with respect to K. And the result is L squared. We keep it here as the constant multiplier, and we are looking for the derivative of K squared with respect to K. The result is 2K of this derivation. So the total result is 2K L squared. We just rearrange the order to be consistent with the above. That will make the following calculation easier. The following calculation in 3, okay? So question 2, what is the expression of the iso cost curve? So C equals to total cost is composed of the total cost spent on hiring labor and the total cost spent on purchasing facility, right? So in which W is the cost per each labor, and here L is how many units of labor you hire, R is the unitary cost of capital, and K is how much capital that you hire in total. And here C is an open question because we seek to minimize cost. So that is not determined yet. Now, question 3. What is the expression of the tangency, namely optimal rate of substitution between K and L? So here, that one, we're going to refer to the the gold rule, in which it is marginal product of which producing factor over the price of which production factor, right? So it's marginal product of labor over the price of labor, which is W, marginal product of capital over the price of capital, which is rent. Then we just replace them. Marginal product of labor is 2K square L over the wage, which is 4, equals to marginal product of capital, 2KL square over the rent, which is 8. And then we just need to reshuffle this a little bit. So here we have the common term 2 on both sides of the equation. We can cancel them first, and then we do cross multiply. We have 8K square L equals to 4KL square, right? And here we can divide 4 to each side of the equation. We have 2K square L equals to KL square. And here we have an additional common term to divide, which is K by L. And then the left-hand side is 2K, the right-hand side is L. So that's the optimum. And now number 4. What is the firm's optimal decision on K and L under this price ratio if a production plan of 40,000 units needs to be satisfied? So here, Q bar, which is the targeted output, is 40,000 units. And here, how did you produce this? Through Q of K and L, which is L K squared L squared. And because of this start function that you saw above in question 3, L equals to 2K, so we can replace. So we have K squared by L, which is 2K squared. So we have K squared by 4K squared, which is the square of 2K. The result is 4 by K to the power of 4. Then we solve for K, right? We divide 4 to both sides of this equation. So here we have 40,000 equals to 4K to the power of 4, right? Then 10,000 equals to K to the power of 4. So K equals to the 4th square of 10,000. So K equals to 10. And then the optimal L equals to 2K according to the star condition, right? L equals to 2K. So that equals to 2 times of 10, which is 20. So here we have the result. Thank you.